So in queue data structure, we would have two pointers which are basically active pointers. Unlike a base pointer last time that we had no use of it, but this time we would have two data pointers and they both will be used. As in I said that front pointer is required to delete the data. Walaikum assalam Ali Hassan. And the rear pointer is required to insert the data. So front pointer is used to delete and rear pointer is used to insert the data. Okay, rear pointer is used to insert the data. Now instead of making this array vertically, I have shown it horizontal. Okay, there is no difference in stack or otherwise. Whenever we discuss array, we use array vertically. I have just shown it horizontally, so that really does not matter, but I have just done it to make it alike. All right, so make it like Q. So we would have two pointers, the front pointer and the rear pointer. Okay, and we will move rear pointer when we are inserting the data, and we are moving front pointer when we are deleting the data. This is something that you will have to actually remember. Now, so front pointer is to delete, rear pointer is to insert. So when we delete, I have seen in a book, the course book that we have, we call it DQ, and when we insert, we call it NQ. Remember, these are not formal terminologies, and these have never appeared in exam. In exam, rather, we would have remove or delete and insert or add item. All right, so remember. Now, let's say this is the situation that we have got nothing removed from the queue and all we have is added things. So whenever we are adding, like top of a stack pointer in the stack, we are moving the rear pointer ahead. So if we actually remove or we dequeue one item, that would be the item that was actually entered first. All right. So the operation or the principle of operation for the queue is what? First in, first out. So the first item that was entered is 27. Then rear pointer moved further for the next item, then further for the next item. Now, as I said that we use front pointer to delete. So we will delete from the position at which the front pointer is basically pointing to. So front pointer is now pointing towards zero indexed element, and that is 27. So since the 27 was the first entry to the queue, it will be removed and the front pointer will move forward. So we dequeued 27. Now in in 3, we added couple more. So we enqueued 31 and then we enqueued 55. And then we dequeued, and what was dequeued? 34. So the front pointer moves forward. All right. So this is what the mechanism of the queue. So you have to remember one thing, and that is basically important. That is that both pointers are moving forward. So it's like when an item is added, rear pointer is moving forward. Item 1, 2, 3, 4 added. And as the operation said, remove in order of entry, then the front pointer will start removing and it will also go forward. So they both are moving forward. If at any given point they both point to each other, that means what? It means that Q is now empty. Since rear pointer is moving forward to add and front pointer is moving forward to delete, at any given point, if they both are equal to each other, it means simple that whatever the item those were added to the queue are now removed. All right. Now, now the pseudocode for simple queue. QADT. So we will have basically front pointer, rear pointer, and upper bound. Upper bound of what? The array that we are going to create, which is in this case is 10. So that we could match when we are entering the data from the rear pointer. If the rear pointer has reached to upper bound, it means that we cannot add any more data and overflow occurs. So in this case as well, with the queues, we would have same two errors possible. The one when we are not having any spaces or locations available to add more item to the queue. In that case, we say that this is overflow. And similarly, if we don't have any item in the queue and yet we are trying to remove it, in that case, or we are trying to dequeue it, in that case, we call it basically underflow. So we have these three variables, and these two pointer out of the three variables are declared in the global space so that they are available to all of the subroutines, and an array which is from 1 to 10 of character data type, and we name this array as q. We are going to use this array basically as a queue. Now, first the procedure to initialize the queue, and we will initialize front pointer to 0, rear pointer to 0, and upper bound to 10. And then we run this loop with the pointer I. This is a count based loop, and we will initialize every single position of, or every single element of the array Q. So this is initialization, and then we have enqueue. Enqueue means adding data to it. Now, this enqueue procedure is expecting a data item that is required to be added to the queue. So it is received as a parameter. Now, the first thing that we have to check if the rear pointer is the pointer which we are using to add values to the queue. So if rear pointer has already reached to upper bound, in that case we will output there is an error which is overflow. If it is not, then we move the rear pointer forward, and at that new location of the rear pointer we will add the data. That's it. That is very simple. Okay, so if the rear pointer is at upper bound, we cannot move it any further, so we will give this error. Otherwise, we will move the rear pointer or increase the rear pointer by 1, and we add that data which is received as parameter to that rear pointer location. And then we have got dequeue. I told you that since both pointers, the rear pointer which is adding the data and the front pointer which is deleting the data, they both are moving forward, and if they both become equal, in that case there are no more values. Since rear pointer was adding and front pointer is deleting, when front pointer deleting has reached to the position of the rear pointer, it means that they both are now equal and there are no items. All the items that were added are now removed. So if the front pointer equals rear pointer, in that case there is an error, underflow, they don't have anything. How would they return anything? Okay, so in this case, unlike stack, I have not used a function that you can always, rather this procedure itself is outputting. All right, so front pointer moves forward, and whatever the value that is at forwarded location will be output. It means that this new location where the front pointer is now pointing to is removed. All right, so this is very simple code. Now, let's see a program for it. So this is a simple program. Enter the data to add in queue. So let's say A. Front pointer is equal to 0. Rear pointer is now 1 because it has reached A, and then queue size is now 1. How many locations do we have? 1, 2, 3, 4, 5, and 6. All right. So front pointer is still 0 with where it was initialized, and then rear pointer has moved forward. As I said, the rear pointer is used to add the data. So now we have added B. So now you can see that after A, B is added, rear pointer has moved another location forward now, and the queue size now is 2. And then enter data in QC. Now you can see that A, B, and C are added, and the rear pointer has moved forward. And then D, another item is added, then E, another item is added. All right, and enter data to add in QF. All right, so now what they have done, after we added F, the rear pointer has reached 5, and F, acha, we had only 5 values there, sorry. Q size is now 5, we cannot add F to it. And then A is removed and B is removed. A and B both are now deleted. So front pointer has moved forward, front pointer is at 2 now, and rear pointer is at 5 now. So that is how it actually works. Instead of presenting with the menu, we have used it differently. So let's see if there is anything else that I have to show to you. All right, this one is sort of what we have done with the stack. So here we have a start pointer as an uh, rear pointer and end pointer as a front pointer over here. And then we present with the push and pop and reset the queue thing. And then we have push, pop, and reset. Reset as an initialization of the queue. If the start pointer is equal to end pointer, when we are actually removing or popping the value, in that case we would have underflow. Otherwise, we just write the value and move the end pointer forward. And for the push, we actually enter the new value right there. We are not accepting any parameter over here. So there might be several ways writing the code. So this is basically queue. So I hope that you would have a fair idea of queues now. Let's discuss yes, Mohammed Moazzam. These will be available. These will be available with the same link. All right. Now the last data structure, which is basically linked list. Linked list is a little more complicated than queue and stack. and are a bit challenging. Next year, since you will have to actually write code for the same, these will become the ones which are more challenging than other data structures. All right, although you would have several data structures in P4, but this one will be a little more complicated. Why it is little more complicated? Because the rules attached to it are not as simple as a stack where it says that last in first out, or queue which says first in first out. There are more things attached to it. So in order to cater with all the demands of the linked list ADT, we would have to write a little more code. And when there are several rules, it means that we would have to write complex code. Anyways, whatever it is, we have to make our concept clear this year. And next year, we will write codes for it. All right. Now, what are the key terms and what is basically the linked list? Linked list is actually a concept which in few of the languages are available as an actual data structure. Means you can create a linked list, like you can create or declare an array or a variable. You can also declare a linked list, but in our syllabus this linked list itself will be um, also made using the array. So now that part, array and all, we will do it later. Let's first clear the concept that how basically linked list is made. First thing that you have to understand, unlike array where all the elements are present adjacent to each other in one memory area, and we use an index. Why do we use index? Because they all are present next to each other. They are connected. All the elements in the array are connected. Means after 0 there is 1, after 1 there is 2, after 2 there is 3 index, and that is how the whole array is presented and made and declared and is available in the memory, all in adjacent memory locations. Whereas the concept of linked list is bit different. In linked list, we only have a new element when we have a need for it. In array, we think of the number of elements beforehand and we declared an array as big. And then during the execution of program, if we like to decrease the array because we might have made it bigger than the requirement, we cannot do that unless we kill the program and readjust the code. Or if we have made it bit smaller than that is the requirement, in that case we cannot actually increase the size of the array during the execution of program until unless we stop the program and we go to the code and we check it. But in that case we might lose the data that we have acquired in the array. Unlike that, where the array is basically static in nature, means once made cannot change the size during the execution of program, a linked list is dynamic. By saying dynamic, what I mean is that whenever you require to add another node to linked list, here we don't call it element, rather we call it a node, we can always grab a little more memory from the available main memory and we can use it to store the next data item. And if we don't need it, we can release it while the program is still being executed. And other programs, while our program is still working, other programs can use that released memory for themselves. That is what is the dynamic linked list means. But as you can understand that the memory that we have, the main memory, it is basically random access memory. What does it mean? In static data structure like array, where all the memory is present at one location and it is divided into elements and can be accessed using index, we are not going to have all the nodes in the linked list together. So we are only acquiring it by requesting to the operating system through the language that we are using when we need it. So if we are needing it, when there is more data to be saved, we request to the operating system. Operating system analyzes the random access memory, and wherever it finds as much free space, it allocates that space to us. So it means every time we grab a node to store more data in it, that node is from any unpredictable memory location or the random memory location that is just being given to us by the operating system. So all the nodes in a linked list are scattered all over the memory. They are not available in consecutive memory locations. So naturally, we lose that connection that we have intrinsically, naturally in array, that after index 1, there is index 2, after index 2, there is index 3. Rather, in this case, we would have to keep a record of it using a pointer variable with every node, that where is the next node available in the memory. So when the list starts, it might have first node in location 1001. At location 1001, we will have to store where the next node's location is. We would have to have a pointer attached to location 101, 1001. That might say that 3057. And then we jump all the way from 1001 to 3057. And then at 3057, we would have the next data item and a pointer to the next node. And this way we will be jumping throughout the random locations in the computer's memory in order to handle our data structure, which we call linked list. Why do we call it list? It's a list because all the items that are saved are in the form of list. And why it is linked? Because it is actually using a pointer to the next available location. So conceptually, if we look at it, there is a start pointer which tells that where is the next list location actually present. So we follow that start pointer and we reach out to the first node. A node has got two parts, the data part and the pointer part. The data part, what is saved at this particular location, and the pointer part is now pointing to the next location, next node's data. So now B is pointing to this node, which is somewhere, although it seems that they all are in a sequence, they all are in a line. No, they are not in a line. They are all scattered around the memory. And that is how when the next pointer is null, null is being presented like this, a 0 with a cut in it. Unlike pi, don't call it pi or whatever, this is a null pointer. So this is the conceptual diagram of a linked list. So what are the terms that we are looking at? First of all, it is node. It is an element of the list. This is a node, a pointer, a variable that stores the address of the next node it points to. Null pointer, it means that this is the last node and there is nothing afterwards. And if we acquire another node, in that case, we will replace this null pointer with that new node's address, and in that new node, we will make the pointer null. And then there is start pointer. This is a variable that stores the address of the first element or the node of the linked list. So what do we have to keep in mind? The rules. All elements, node data should be inserted in order. Now, this is something which is challenging, which I had termed as challenging. That whenever there is a new node added, that node has to be in a sequence. Means if I add A, that should be before B. If I add C, that should be between B and D. And if I should add M, that should be after L. So that is how we maintain the order of the nodes as per the sequence, increasing sequence, ascending sequence of the entered data. Well, that might not be necessary, but as per your syllabus, it is. And right from the beginning, even in A2s, in P4, whenever there are questions, those questions are with this understanding. So we call it ordered linked list. There might be other type of linked list in other syllabuses or syllabuses ahead of A-level in university and or in undergraduate programs. But over here, it is an ordered one-way simple linked list. What does it mean it is one-way linked list? It means that if you are here, you cannot go back because all of the things that you have is the data and the pointer is only moving forward. So at any given location where you are, you cannot go back, only you can go forward. And at any given point when you are at a node, you cannot tell that how many nodes are there or how many nodes that you have crossed, until when you are jumping from one node to another node, you are keeping a counter variable separate. If you are not, you cannot. So the number of nodes at any given point is unknown. How many nodes that you have climbed until you have reached to this particular current node, you don't know. And this is a dynamic data structure. What does it mean? As I explained, the dynamic data structure means that the data structure which can increase its size whenever it is required and decrease its size whenever that is required as well. All right, so when you need to add more data, you grab a location from the memory, and when you don't want it, you can release it to the memory. Whenever a node is deleted, it will be made. Acha, we will discuss about further rules later. So conceptual diagram of a linked list that you have seen over here, this is just the concept. And remember that we would have to actually apply this concept using the array. So let's say this is the original linked list and we are amending it at every stage. Not amending in consecutive order, but amending from the first to this current point. So if we like to add a node at the start of the linked list, we would have to alter the start pointer to that node, and that node will be pointing to the previous first node. So conceptual diagram, adding a new node to the beginning of the linked list. As I said that it is ordered linked list, the data that is being added should be at the start. All right, then what if we like to add the data which is in sequence happens to be present at the end? Then we have to actually remove this null pointer, and we will point that pointer to the newly acquired node, and then in that particular node the pointer will be null. So adding a node to the end of the linked list. And then deleting the first node in the linked list. So earlier it was pointing to this B. Now since this B is deleted and released to the memory, the start pointer will be pointing to D. So the start pointer is now pointing to D, D to L, and this B is now gone, it is deleted. This is deleting the last node. So the last node was L, and it was basically pointing to null. Sir, data is inserted through the beginning or the end. No, there is no such thing as the beginning or the end. We would have to actually climb every node from the start till we reach to the node where we now will have the data afterwards. So let's say if you like to add C, we would have to climb to B, and then standing over here, since we have a link to D, we will check the item in the next node, and we see that that is basically bigger than the C that we want to add. So at B, we would have this idea that the next node should be C. So we would have to write the code so that we could point now to a newly acquired node which is having C, and then this particular pointer will move out to that particular node. We will look into it. So we cannot add from the start or at the end. Rather, we would have to jump to the node after which the new node will be added, and then we do that. So we would have to write complicated code in this case. All right, keeping all those limitations in mind that we have just discussed, that we cannot go backward, we have no idea of how many nodes are there, and all of that, and it is an ordered linked list, we would have to actually jump forward until we find a location after which the new item will be added. So if we like to delete the last node, we would have to reach at the node after which there is last node, and then the current node's pointer will be made null. Now, adding a new node into a linked list in the middle. So this is sort of insertion. So where B was pointing earlier, that is being copied to C. Now C is pointing to D, and B is now pointing to C. Now we are deleting a node from the middle of the linked list. In that case, B, which was earlier pointing to D, is now pointing to L directly, and this way if we start from the start pointer, we will first reach to B, and then from B we will reach to L, and L would go forward or finishes, and that is how we will read or peruse through this particular linked list. All right, now there is something more to it. We will discuss that before we actually use arrays to understand it. And that concept is the concept of the free list. Means alongside all the lists in the computer memory, since this is a data structure, we might have several lists in the memories, but there is one list which is holding all those nodes which are free. So there is two types of data structures: linked list, those linked lists which you might have made several of those, but there is just one which is free. So free list means it is holding all the nodes which are freely available in the computer's memory. Whenever we require to acquire a node, we will take it from the free list, and whenever we need to delete a node, we will delete it to the free list. So free list is holding the nodes which might be taken by the other lists. So let's say if the free list itself get emptied, it means there are no more nodes available, memory is full. So whenever we need to have one more node, we will be taking it from the free list. And whenever we are deleting a node, we are actually adding it to the free list. So all the lists in the computer's memory are actually acquiring or taking or borrowing nodes from the free list, and whenever they are releasing to the free list. So now let's see new rules, further rules. Whenever a node is deleted, it will be made available at the start of the free list. Whenever a new node is inserted or added to the linked list, it will be taken from the start of the free list. What does that mean? It is clear. Like your start pointer, there is a pointer with the free list itself. So the start pointer of the free list, which is called free pointer, is pointing to a node, which is the node that you would have to actually acquire if you want to have another node. So free list is a list of all the free memory nodes available. Until or unless there is physical memory available to be acquired, that is part of the free list. If free list becomes emptied or null, it means that there is no more memory available. So whenever we are deleting, the node that is being deleted will be added to the start of the free list, and whenever we are actually adding, the node that is being added will be taken from the start of the free list. Now let's conceptually watch that idea. So this is the conceptual diagram that we have got a list, which is, let's say, list 1, that is having, now I have made these memory locations which are sort of random for your reference as well. So the start point is pointing to 2, node at 2 is pointing to 1, 1 is pointing to 0. All right. So they are in order of the items added to the content, to the element or the node. So this is the situation. So this is 3, this is 4, this is 5. So whenever, let's say, this is what adding a new node at the beginning of the linked list. So as I said that whenever the new node will be taken, it will be taken from the start of the linked list. Which linked list? Free linked list. So free list is now pointing to the next node. Start pointer of the list 1 is pointing to the first previous node of the free list, and then that is pointing to the B. So a start pointer which was pointing to 2 earlier is now pointing to 3, 3 is pointing to 2, and then free list is now pointing to 4, where it was earlier pointing to 3. All right, so whenever we take a new node, we will take from the start of the free list. Afterwards, we are adding a node at the end of the list. So as I said that whenever we take a new node, we will take from the start, even though this node will be available at the end of the list 1, but it is a node that was taken from the free list start. So now free list is pointing to this location, and this list is now have taken the first node from the free list. Now this node from the list 1 is deleted. Now start pointer is pointing to D, and this B which was deleted is now part of the free list. But as I said that whenever we delete the node, we will add it to the first of the free list. So deleting the first node, that node is now the part of the free list start. So now free list is pointing to B, and B is pointing to the further nodes. Deleting the first node of the linked list. All right, so if it is deleting the first node of the linked list, the start pointer earlier was pointing to 2, and 2 was pointing to 1 and all. Now free list is pointing to 2, 2 is pointing to 3 and 4 and 5, and start pointer is now pointing to 1, and 1 is pointing to 0. As you can see, this is the first node deleted, which has become the first node of free list. Now this is the last node deleted. Earlier start pointer was pointing to 2, 2 was pointing to 1, and 1 was pointing to 0. Now the 0 has been deleted, and as I said that the rule says that whatever the node that is deleted will become the part of the start of the free list. So this L has now the part of the free list at the start. So free list is now pointing to 0, 0 is pointing to 3 and 4 and then 5, and whereas this start pointer is pointing to 2, and 2 is pointing to 1. So this is deleting the last node and making it part of the free list start. Now over here, adding an item in the linked list. So we have added one C item. That C has to be by rules, as the rules say that the data that is being added should be where it is expected to be in the sequence. So the C is now required to be between B and D. So start pointer is pointing to B, B is pointing to C, C is pointing to D, but if you put C, that C is the first node of the free list that is now taken from the free list start. So start pointer, then the previous. So this is the start pointer now pointing to 2, 2 is pointing to 3, 3 is pointing to 1, and 1 is pointing to 0, whereas free list is now pointing to 4 and 4 to 5. Free list, deleting an item from the free list. Sorry, from the linked list. So this D is now deleted, and as the rule says that whatever will be deleted will become the part of the free list at the start. So now this free list is now pointing to D, D is pointing to 3, 3 is pointing to 4, and 4 is pointing. So free list is now pointing to 1. So this is a concept that you have to make sure that you know it, that the linked list is in order. Whenever you take the node from the free list start, and whenever you delete a node, you actually make that deleted node part of the free list start. All right. So now let's see that, sir, the free list concept number 4, 5, 6 dobara samjha. Okay. In 4, we deleted B. So B has become the start of the free list. So start pointer is now pointing to D. Earlier it was pointing to B. That B has become the part of the free list. So now free list is pointing to B, which is 2, and 2 is pointing to the 3. In 5, this last node is deleted from the linked list. So it has become the first node of the free list. So free list is now pointing to 0, 0 is pointing to 3, 3 is to 4, 4 is to 5. So any node, whether it is second or the last or first or whatever in between, whenever it is deleted, it will become the part of the free list start. In 6, we have added one new node to the linked list. So that node will actually be the first node of the free list. So we have taken C from the start. Okay, that is how it works. All right, now let's see how do we actually achieve it using array. Now you need to understand one thing. In array, we will be using UDT, the record data type. All right, UDT, the record data type that I had taught you in earlier lectures, where we define our own type, and out of that UDT we create arrays or variables. Now this is an array which is basically sort of 2D array, but actually it is UDT array. Start pointer is pointing to 2, 2 is pointing to 1, and 1 is pointing to 0 index. So these pointers are basically pointing to the index. Now this is an array without free list implementation. So first you need to understand this, and then we will use the free listing. So why it is pointing to 2? Because 2 has got the data which is the first in the sequence, in ascending sequence. So 2 is basically B, B is pointing to 1, which is D, and then L. So B comes first, then D, and then L. Now we have added a node at the start. So we have added A over here at 3. So instead of now pointing to B, we are rather pointing to A. A is then pointing to 2. So 3 is pointing to 2. So this is the node. Node is having an index. This index is being used as a pointer. So start pointer is 3, which is having A. A is pointing to 2, 2 is pointing to 1, 1 is pointing to 0, and 0 is pointing to -1. So that 0 with a cut in it, we cannot place it over here. So we use, if the start of the index is 0, then we use -1 as the null pointer. Or if we are starting from 1, then we use 0 as the null pointer. Now, this is adding a new node at the end. So end was L. So we added a new node P. So we are now pointing to B, B is pointing to 1, which is D, D is pointing to L, which is 0, and now L is not pointing to -1, not null pointer, rather it is pointing to the last node, which is P. P is now pointing to -1. Deleting the first node. So when it was actually B, B was pointing to 1, now we are pointing to 1. So B is deleted. So start pointer is pointing to 1, 1 is pointing to 0, and 0 is L, which is pointing to -1. Okay. Now we go further. That is how we control it. Now let's add the concept of free list. So the first thing that you would have to understand, when there is no list, it is just the free list. When there is all the lists which are empty and no items are added to the usual list, it is just the free list which is having all the nodes. To keep a track of all unused nodes, a technique is to link all the unused nodes into the free list. So this is now important, that you might be asked, because it is all about concepts in past papers, or what I am actually expecting, that you would have one array given and they will ask you to set up this array for the list. Now you can see when there is no list, it means that start pointer for the list is either -1 or 0. And free list is now pointing to 0, 0 is pointing to 1, 1 is pointing to 2, 2 is pointing to 3, 3 is pointing to 4, means when there is no data, all the nodes are the part of the free list. So free list is pointing to 0, 0 is pointing to 1, 1 is pointing to 2, 2 is pointing to 3, 3 is pointing to 4, 4 is pointing to 5, and the complete number of nodes are actually part of the free list. When you add items, now you can see that start pointer is pointing to 2, 2 is pointing to 1, 1 is pointing to 0, and 0 is pointing to null. Free list is pointing to 3, 3 is pointing to 4, 4 is pointing to 5, 5 is pointing to 6, 6 is pointing to 7, and 7 is pointing to -1. Now this one array is having two lists. All the items which are utilized are part of the list, and all the items which are free are part of the free list. All right. So if you add the item at the beginning, you will be adding the item where the free list is pointing to at 3, because this 3 will be treated as the start of the free list. So you will add 1 at 3, and then free list will become where the 3 was pointing to. So 3 was pointing to 4, so free list has become 4, and the item that was added is now being utilized by this particular list. So this is pointing to 3, 3 is pointing to 2, and onwards until -1, whereas this free list is pointing to 4 and 4 to 5, and all the unutilized, unused nodes are now the part of the free list. Adding a new item to the end of the linked list. So again, it is pointing to 2, 2 is pointing to 1, 1 is pointing to 0, 0 is now pointing to 3 where the last item is added. So you need to understand this concept. If you like to sort items in the list without moving the items, as we would have done it in bubble sorting, where we kept the index the way it is and we actually shuffled all the array elements data. Here we actually manipulate pointers to keep the sequence. We do not move the data. Data is where it is. All we do, we basically make the whole list in a sequence by manipulating pointers. All right. So this is the concept. Now, inspired by the past papers, at the end, we have got this list. All right. I will explain this afterwards because you might be asked to set up a linked list. So what do we do? Right at the start, when there are no items added, what we would do, we will make the whole array as the free list. So the start pointer will be pointing to 0. Start pointer will be pointing to -1 or 0. And free list will be pointing to the first element of the array. And then that is to the subsequent elements until we reach at the end, their free list finishes. So this is the concept of all three. I am deliberately using no pseudo code and no program code for the linked list over here, as it is not required by AS, and that will further indulge you into something unnecessarily tedious or complicated, which is not required. All right. So it is a good idea just to limit yourself as far as this linked list is concerned to the concept. And in the next class, Sunday morning, we will discuss the past papers related to the concepts of all three ADTs which are part of your syllabus. If there is any questions, please do ask. Otherwise, I'm going to wind up this. You can find all these boards over the GitHub. You can find all these boards over the GitHub. My GitHub handle is github.com/ZAK These boards are available. Whatever the board that I have shown are all available there. Any question?